I see that attendees are joining, so maybe a little bit we can wait.
Sure.
Okay, let's get started. Hello, everyone. I am Yalda Mohsenzadeh, and I will be moderating this session. Our guest today is Dr. Gemma Roig, who is a full professor in the Department of Computer Science at Goethe University Frankfurt. Gemma, before that, was an assistant professor in the Singapore University of Technology and Design. And prior to that, she was a postdoctoral fellow at the Center for Brains, Minds, and Machines at MIT. And she received her degree from ETH Zurich in computer vision. Her research is interdisciplinary, and it tries to understand the underlying computational principles of visual intelligence in humans and AI systems with the goal of developing general AI frameworks. So we are very excited to have you here, Gemma. Thank you for joining us, and we look forward to hear your talk.
Yeah, thanks, Yalda. It's a pleasure and honor being here and being able to talk about some of my work with you all. So I'm not sure if I'll be able to track the questions along the presentation, but please feel free to ask along the way and I'll see if I can answer.
So like we can, like I asked the audience to put their questions in the Q&A, and then after your talk, we can go over them and discuss them. But I ask attendees, please feel free to write up your questions as we go through the talk so you don't forget.
Perfect. Excellent. So yes, as Yalda said, I am Gemma, and today I'm going to talk about unaligning machine and visual cortex representations. And okay, this is the last slide. Very good. So I'd like to start my talk by introducing object classification task, which is the question of answering like what is in this image, which object is present in this image. And here you see just like a sample of a data set that's called ImageNet. By now, probably most of you are familiar or will be familiar at some point. Because it's a very important data set that kind of also sparked these new advances in AI and also in computational neuroscience. So for tackling this task, there has been like a great advance in 2012 with the introduction of this AlexNet network based on deep learning. And then over the years, there have been also more advancements in these directions, making the deep neural networks either deeper, wider, and changing some facts of the architectures that you see in the last one, the visual image transformers, which are not convolutional neural networks anymore, but based on self-attention layers. And here what you see is really the striking result that the deep learning approaches obtain with this ImageNet dataset that I introduced you at the beginning. So before using deep learning networks, mostly convolutional neural networks at the beginning, so the error rates were quite moderate. But then in 2012, with this AlexNet, the error rate was dramatically reduced. And then after that, the researchers in the field started just to use more and more this technique to have better image classification results. And of course, we know that specifically convolutional neural networks were inspired by how the visual cortex processes images, specifically like the localization of the processes, starting with filters, for instance, and then building up representations through a hierarchy. So they took the opportunity also that even though these models were developed independently from how the brain works, to bring them back and see how those could be used to really understand the brain and what are the processes that are being done while observers, for instance, see some images. And here you see one of the earlier works that showed that taking a model like AlexNet, which again was developed independently from understanding the brain, could actually explain a lot of the brain data variants much more than handcrafted models to targeting this scientific question. So along these lines, and pushing more the boundaries of this project, so there have been some efforts in which also emulating these challenges of predicting or solving a task with then giving a particular score and so on. So there have been some efforts in putting up challenges also in computational neuroscience, and not only in, for instance, computer vision, like the ImageNet challenge. And one of them is this Argonauts project and challenge, which I've been co-organizing since 2019 with several other people. And we envisioned this as a project in which we could build a platform for explaining the human brain with algorithms, in which participants would submit their models and their algorithms to explain particular brain data that we would curate and that we would also design some score. So for instance, in 2019, we had the visual brain. So it was mainly for object categorization. And we had fMRI and MEG data with a small reduced image set. And then we used RSA that I hope you are familiar with as a metric for aligning brain and model representations as benchmark. And then we moved on in 2021 to include motion. So we recorded fMRI data in this, putting humans in the scanner for a large video set, so more than 1,000 videos. And then this time we used as a benchmark to setting up who was the winner of the challenge with encoding models using the percentage of variance explained. And just recently, last year in 2023, we had another one, which is we use NSD, so the natural scenes data set. And this time it's like even larger data set with very high quality and also use encoding models. So we had the typical setup of the challenge, like with winners and a workshop, inviting people to present their methods, and then we could discuss how to move forward. So just to give you a little bit of a teaser, so there will be another one in 2025. Probably it will be released in October, October, November. And it will be also videos, but using TV series. So we envision that probably the models can be even more interesting beyond just images and short events. And it will be fMRI and also with encoding models. So just keep tuned. So along these lines, also going beyond objects, so what we wanted to ask, so object recognition, we wanted to explore ourselves in our own research. Let me see if I can get rid of that. Here, just 1 second. Maybe I can just move it. Okay, no, I cannot move it. So what we wanted to do is to explore different vision task representations in the brain using also model representation. So mainly our question that we pose is, can we assess function of brain areas by computing these correlates of the responses of the models of the brains to a large set of diverse models trained on different computer vision tasks. So going beyond only object categorization, but also including other visual tasks, which could be, for instance, related to 3D information, so how far an object is, or if there is an occlusion, or how objects are grouped, and so on. So how we approach this? So we had an stimulus set that was used both for recording the fMRI responses of subjects, of humans, and also get representations of task-specific DNNs activation of trained task-specific DNN. So what do I mean by task-specific? So we had a set of DNNs, each of them trained on different tasks. And here you can see examples. So for instance, the first one that you see is the texture edges, like detecting texture edges or surface normal or scene classification, also, of course, object classification, room layout, and so on. So one model per task. And then what we wanted to find is how the representations of each of these models relates to representations of the brain in particular areas or in a search light analysis fashion. And then get a ranking of it and find, okay, the representations of the models that can predict or that correlate better with the brain representations will be the ones that are more related, so we can link particular brain regions to the function that the model has been trained on. So for the evaluation of the DNN fMRI comparison, the representation level, we used what is called weighted RSA. So mainly what you do is given some input, here is X, so it's an image, you pass it through the model on one side, or you show it to the participant in the scanner on the other side, and then you get representations either from the model or the subject, and then you find the representation using RSA. So you compute the RDMs for the representation of the model, the RDMs for the representation of the fMRI responses, and then in this case we use a regression because we use two kind of representations of the model, which is the last layer and the previous one, which is the most task related, but this is just a detail. And then we can obtain a ranking and compare different models on how they can predict or explain the variance of the fMRI data. So for this, what we need, of course, is a set of models that have been trained with the same data set, that have the same architecture, and the only variable that changes is actually the task they have been trained on, because then we can just take into account this variable and validate that the function is actually the factor that really leads better explanation of the brain data. So for this task, there is this data set, which is great, which is the taxonomy data set that also provides task models. So it contains also more than 1 million images that are annotated in different tasks. So you can predict the output from one image that relates to colorization, denoising, key point, detection, reshading, object classification, and so on. So you can have one model as a proxy of one of these functions, and then get the representation level that will relate to this function. And this is on the model side, and then on the fMRI data side, we had our data from a collaborator, Mick Bonner and Einstein data, that they use these indoor scenes that are disjoint from the taxonomy dataset, but still from the same data distribution, because both are indoor scenes that they use for studying navigational affordance in an fMRI study. So they had individuated also some particular ROI, so they had localized them. The ABC is the early visual cortex, so PA, PPA, and RSC are scene areas, so scene-related areas in the brain. And what we wanted to do first is to see like which kind of functional map of the whole brain we get when we do a search like analysis with these task-specific DNNs with the weighted RSA, to see, first of all, if the pattern is consistent and it's not random, also if the task is relevant. So for instance, we also took as a baseline a random DNN, which is just like taking the architecture without any training. And what we see is that the random DNN doesn't show anywhere. So the second observation that we have is that the models that are related to 2D tasks, like for instance, detecting to the edges, key points, and so on, mainly correlate the most in the early visual cortex, which is also something that is well known in the literature. And we also have the TNN representation related to the 3D tasks, like for instance, surface normals, or how far is an object from the camera, and so on and so forth, in the dorsal regions, which one could loosely say, okay, this is like the where pathway in a way. And then the semantic DNN, so where the semantic information is, so what kind of object or what kind of scene it is, it's more in the ventral regions and some of the dorsal. So here I have to say that this was just selecting like the model that gives the highest correlation, like there is no statistical analysis because we had 20 models, that's a lot. So what we did also separately is check the nature and the predictive power of this functional map by getting different brain regions with an atlas and then predicting by subject. And what we could see is that the variance explained in 9 of these ROIs is above 60% of the lower noise ceiling, which is actually highly predictive as well. So what we can see with this method is that different regions in the brain explained by these DNNs performing different tasks can unveil functions of brain regions by comparing with these multiple task-specific models. And then consistently with the literature, so early regions better explained by the 2D models, so models that predict 2D functions like edge detections. There's dorsal regions by the 3D models, and the ventral regions by the semantic DNNs. And then this method also has like a high explainable variance, at least in 9 of the ROIs that we analyze. So it has a quantitative power that it's quite remarkable. Okay. And by the way, we have the code and the data. So if you would like to use parts of it or revalidate our results, so it's all there. So another thing that we also tackled is that, so I showed you that this approach can do like a searchlight or a particular ROI analysis with these models. And this is to localize, so where in the brain particular functions are being processed. But this could also be applied in the dynamics, so unveiling how the functionality changes over time. So what we did is to find a functional mapping in time with EEG data. So we took the same stimulus set that we had used with the fMRI from our collaborator, and we recorded the brain activations with EEG. So here are just some of the details that we use. So we had 16 subjects, 75 repetitions for each image with 15 runs. And then we had the task of asking the subjects if the arrow was pointing to the same direction as the navigational path in the previous image. Okay. So how did we do that? So actually, the same exact methodology can be used, but instead of taking the location in the brain to compute particular RDMs, one can take the location in time. So compute the representation dissimilarity matrix for each time window that we want to analyze, and then do the same process again. Okay. So we get the model representation dissimilarity matrix in the same manner as we got before, but here what we did, that we also did in the previous study, but I don't have time to show you, is to merge all the models that were representative of the 2D functions with some technique that we use to validate that this is the case. The ones with the 3D functions and the one with semantics, so we can distinguish when 2D information is processed, when 3D information is processed, and when the semantic information is processed in the dynamics. And then we also use a behavioral model that is the navigational affordance model that was actually proposed by the original paper that used this, the original fMRI data, because they were interested in navigational affordance. And in this case, we also use it for as a comparison. So that's the metric that we use for the alignment here. So as I said, we compute the RDM for each time point in the EEG signal, so windows of 10 milliseconds. So we have one RDM per 10 milliseconds. Then we have the RDMs for the DNN models that we combine. We have the 2D, the 3D, the semantic functions, and then also the navigational affordance model. And with this, what we do is we compute the unique variance. So I didn't explain it here, but the unique variance mainly is very similar to the RSA, but instead of just taking an absolute value of how well one particular model can correlates with this, the RDM of a particular model correlates with the RDM of the brain data. So in this metric, in the unique variance, what you do is you regress out the contributions of the other models that you are comparing to, so you can obtain the unique variance. Okay. So how uniquely you can explain factoring out the other models, what they bring to other models. So here what we see is in blue these unique variants with the 2D DNNs, in some green the 3D, and then the semantic and the navigational affordance. So if we analyze the peaks, and here you can see it in the right-hand side of the plot, okay? So the 2D DNN shows the earliest peak, which is kind of expected. Also, it's reported previously in the literature, followed by the 3D and the semantic DNNs very closely, even though there is a bit of statistical significance in when it peaks. And finally, the navigational affordance model, which is the latest. So with this, what we suggest is that the visual features are processed before the navigational affordances in the human brain, at least in our setup. And actually, this has been a discussion going on in the literature if it happens simultaneously on one thing after the other. So in our experiments, what we see is that the representations of extracting 2D, 3D, and semantic features are potentially used for behavior. So what we see is that the correlation between the DNNs with the brain area, and this is with fMRI, and the time response that we got with the EEG depends on the task that the DNN was trained on. So the DNN models can be a potential alternative to gain insights for assessing a brain area's function, or when something is processed in the brain. And then what we are doing, of course, is considering fMRI datasets with that have greater coverage, and this links to the Argonauts project, as you can imagine, and also consider more complex tasks than single static images. And now we are also using videos that can maybe potentially give more richness to how we can do the analysis. So also to bridge the AI modeling and the computational, cognitive computational neuroscience, we are developing this toolbox that we call Net2Brain, which is a toolbox to compare artificial models. It's not only vision anymore, we have also LLMs and multimodal models with human brain responses. So it's for facilitating this intersection of the cognitive neuroscience and AI research, as I said. It provides functionality for comparing representations of deep neural networks and brain activities. And we have RSA encoding models the unique variants, so all these functions that I talked about already embedded there that can be used. It is Python-based and open source. And we are constantly including more data sets and DNN. So some of the data sets that I talk about are already accessible from the toolbox, but it's also very easy to merge your own data set and your own model. Yeah, and it's already available. So I'll just quickly go through one example of the functionalities of this net-to-brain. So we have implemented a model taxonomy because one of the challenges that we might face is like, so which models do I use for a particular question? And with a model taxonomy, one can say, okay, so I want models that have the same architecture with this particular architecture or a particular task or a particular data set. And then you get all the models that are already embedded there in a table saying, okay, so if you want this particular architecture and this particular task, so these are the available models that we have here. And for the particular example, so what we assess here is the predictive capabilities of different language models. So not large because it's not ChatGPT like GPT, but well, we have GPT-2, not that large. Then we can have like the second step, which is the data selection. In this particular example, we use the NSD, the natural scene data set, the step of the feature extraction. So once we have selected the models, we can get the model representations to compute the alignment on all the models that we have selected. And then we can find this prediction, in this case with linear encoding, but as I said, one could also use RSA or other functions to compute this alignment. And finally, of course, we get some plotting to be able to interpret our results. So here, what you see is some of the results that we got with this, let's say, almost a demo. So we used some different models. So we use BERT, which is an LLM or an LM, using the captions from the NSD dataset because it's based on a dataset that contains captions. And we have functions for parsing this in net-to-brain. BERT with word means that we only take the word of the class. This is a cat or whatever object. And then we also use multimodal models based on CLIP, either the text part or the vision part, and then the GPT-2 also for comparison as a language model. So what we see here is that with the correlation analysis with encoding model, so how it predicts the brain data. So for V1, which is the top left, so the vision model is the one that predicts the best and with earlier layers. And then when while we go through the plot, so from left to right and bottom to down, what we see is the progression of the layers. So what you see for each model is all the layers. So early layers to the left and later layers to the right. So if we see the vision models, we see the progression of the layers and how they can predict the different brain areas, and also how the language models are increasingly predicting with higher predictivity the brain responses along the hierarchy of the brain regions. Okay. So one of the things that is also intriguing is like, okay, we have some intuition of how these models work, and we might understand why this is the case, that there is this progression in predictivity, but we might not know anything or everything because these models are also a bit of black boxes. So another kind of efforts that we are doing in the lab is trying to go inside the models. In particular, here we focus on vision transformers to try to understand what are they really computing and what are the representations representing in a way. So I just want to mention that here there is this work by Martina that she is analyzing vision transformers and how they build up the information along the hierarchy of the model to come up with a decision. And then she can also analyze what is the role of context, what is the role of the actual object for building this final decision. and also like the different components of like the attention layers or the MLP layers and so on. And this method also allows to go back to the input image and then analyze, okay, so this model made this decision and it focused on these particular areas in the image, for instance, and these potentially can also help understand like if there is a particular alignment, so how it really like the attention that it puts here, it might be related to what is being processed also in the brain. But of course, like doing such interpretability is something that is being done in cognitive neuroscience since many years. So that there are a lot of challenges that have been already addressed or discussed in the cognitive neuroscience community that should or that we can bring back to how we can interpret AI models, because it's also kind of like very similar black box thing with very different implementation approaches, of course. So we have also a position paper on what do we need to do, or what are the challenges and implications of decisions for interpreting the models and how we can use these interpretations. So I just want to conclude by saying that there are a lot of efforts bringing AI to cognitive neuroscience to unveil functionalities of the brain or different mechanisms on how the brain processes information, but that we can also take insights from neuroscience or cognitive neuroscience back to AI, both either for building better models or also as methods to try to understand better the models that we already have. And with this, I'll conclude my talk.
Thank you very much, Gemma, for a very insightful talk. And I see already lots of questions and Q&A. So we can go through them. Thank you very much. First. Okay, the first question is about the Argonauts projects, and they ask how exactly is it checked that the models are similar to how the brain works? Are the dynamics of the models somehow compared to the dynamics of the brain? Basically, they need more information about how this alignment test is benchmarked.
Yeah, of course. That's a great question. And of course, this since it's a challenge, we had to make some decisions because we wanted to have one score that could determine a winner. Because we have a leaderboard of first position, second position, and so on and so forth. So in the first edition of the challenge that we had both fMRI and MEGs, what we did is how the model representation, it's not really the dynamics of the model, because the model usually is static. So the only thing that you can do is either you use several models or I mean the participants, or different layers for different brain regions. This they can do. It's up to them. But what we really do is like once they have the representations that they want to compare to the brain, then we either use RSA with the RDMs of model and brain data, or the encoding model. In the later editions, we have been using encoding models for that, because we have like much larger data sets.
Yeah,
so,
like, and the next question is also related to that, asking why you decided to change from RSA to percent variance explained in the next round.
Yes, sure. So I mean, this is a big debate of which metric is better. And I mean, we know that different metrics can give us different insight. Like, for instance, in the RSA, we can have more information about the geometry of the representations. And in a way, it's a bit more crude. And with the encoding methods, you have more like the prediction, the actual prediction, and you have this a bit more flexibility of combining representation. So you assume in both cases that you have two different subspaces, and somehow you need to align them, and these are just two different things. So when we move to larger data sets, so using an RSA has some limitations that you cannot really use the whole set, for instance, and also the way the data has been recorded we also seen that it has a huge impact. So for instance, the amount of repetitions, the amount of subjects and so on. So you have different constraints on how you want to get like a high productivity using one or the other. So since lately we have been using much larger data sets, and yeah, so we've used encoding models.
Mhm. Thank you. And the next question is more fundamental about like what does representation in the brain and model mean? Is it simply some pattern of activations at a single point in time?
Yeah, that's a great question. So in the model domain, this is quite straightforward because once you have some stimulus, you pass it through the model, and a stimulus can be a video, or it can be an image, or it can even be some part of the text and so on. And then you get activations along the layers of the model. So that's a representation in the model. So it's the activations that you get when you process the input information.
Mhm.
In the brain, what we have is really the neuronal patterns that we get either from the fMRI. So, okay, not directly the neuronal patterns if it's fMRI, in particular locations of the brain, which in fMRI is integrated in some interval of time, of course, but it's again, so the representation is the activation that you get as a readout, let's say, when the subject is looking at the stimuli. And if you have like the time domain, then you have the representation that is dynamically changing also over time. And since you have more time resolution, then that's what you care about. It's not more about the particular location in the brain, but where it happens.
Thank you. The next one is, can you give an example of what was explained by these models and what do you mean explain?
Yeah, that's a great question. So, I mean, there are several aspects of that. So, for instance, in the first work that I presented, that we were using different DNNs trained on different functions, on different visual tasks. So, what we use is really the DNNs as proxies of functions. So, this explain is like is the function specific that or selectivity in this case of which particular brain region or where in time this function is being processed, or there is a process that happens leading to the output of this particular function. So for instance, we are edges being extracted or more related to 2D information, or is like the 3D information that is being processed and so on and so forth. So this is one aspect of it. Another angle, which is also related to what a lot of people are doing and what I showed in the net-to-brain example, is another thing that could be, is it more low-level information in the sense of more grounded to vision, or can semantics, because its representations extracted from language models, be more informative, for instance, and how this changes along the hierarchy of the brain. So it depends also on the variables that you change in the model, because at the end of the day, the models are your hypotheses, and you need also your null hypothesis to be able to do this comparison.
Mm-hmm. Thank you. What happens if you have a foundation model which is trained on multiple tasks? Would that increase or decrease the variance explained?
So yeah, that's also a very good question. So I think it depends on a lot of factors. So first of all, it depends on which data we are talking about. So which kind of stimuli we are talking about, which brain areas we are analyzing or doing the alignment on. So it might be that in certain aspects, probably it will increase. So we have seen also that maybe CLIP can be considered a foundation model in a sense, because it's been trained with a lot of data and also on self-learning. So we have seen consistently that these kind of foundational models that are multimodal align better or can predict better the brain responses. So in general, yes, but the important scientific question is why. So we need like some basic comparison of why is this the case? So is it because I also have text and then the semantics are embedded through the visual representations as well? So we can do some comparisons with that, with having like a similar architecture with only visual and then compare this to the visual stream of the multimodal, for instance. Or is this because of the data? So ideally, we could have like another model trained with a different kind of data and then compare this, because also consistently people have reported that the data distribution that has been used during training of the models has a huge impact on the alignment more than the architecture, for instance.
Mm-hmm. Thank you. The next question is, I'm just wondering, is there any computational difference between DNN and the human brain in processing the image statistics of an effective scene and its classification in terms of valence and arousal?
Imbalance and arousal. Okay, so of course, I mean, there are probably a lot of different differences in computation. So if the results are not like 100%, so the model representations cannot really predict 100% of the variance of the data. So there are a lot of differences still that we need to fill the gap. And even if it's 100%, at the representation level might be the same, but we can never be sure that how it got there. So the mechanistic or the algorithm that compute the representation it's actually the same, so that the actual computations is the same, unless we have like a very fine grain analysis of the processes. And of course, the model choice limits you on what kind of computations you are assessing. So if one chooses to use only like an image recognition model, then that's the only thing that you are assessing, and you are not taking into account other aspects like valence and arousal. I think that was the example.
Mm-hmm. Okay, thank you. Is net to brain compatible with intracranial EEG or single neuron data?
Yes, it is.
Mm-hmm. Okay.
As long as you can treat it as I have this data and I can get this representation. So we commonly worked with fMRI, EEG, and MEG, but it is completely transferable and it can be adapted, let's say. And if somebody has troubles, we are happy to help.
Thank you. The next question is a good question. Are the alignment results statistically robust across DNN training runs with examples, different seeds or different data sets for the same vision task? Image, for example, image classification with ImageNet or CIFAR10.
Yeah, so that's a great question, because the data set that one uses for training the networks is actually a variable. So it's not robust to that. And it's really dependent on which data set you use for training the networks, on how much the alignment will be meaningful and will be will have like more predictivity, or will explain more of the variance. And this is something that we have tested. So for instance, just to give like a very crude example, if one is interested in identifying, for instance, objects, and then uses objects outdoors, and then uses only scene data sets that contain no objects that were shown, or similar objects that were shown, and it was all indoors. So the data distribution is very different, and actually the models have only picked patterns during training related to the training set. So this can really bias the results. So one of the things that one, I think, need to consider and be very careful about is like which kind of models and which kind of data one uses. And this is something that one can also test with this hypothesis testing. So you can have like the same data, the same set of models, but only changing the kind of data that you have, and then you can see the differences. This is one thing, and also the task also influences a lot, of course, and we leverage this fact in our studies, right? So this is one of the things that we used for the disentanglement of the different functions in different brain areas.
Did you test any like how the representation alignment would change for various like for different initialization of the model, like as they asked like different seeds
So
across different runs?
yeah. So this is desired, but it is very computationally expensive. So we didn't do that actually. So what we did is compare to the random initialized model, and then for instance, on another project that I didn't present, what we did is to test for different kinds of architectures. So what I mean is that the comparison is always within the same architecture, but then you can do multiple comparisons to see how robust is this two architecture. And then in this case, you can use also smaller architectures and easier to train to be able to tackle the computational cost.
Okay, thank you. What other network models other than DNNs could be imagined to describe biologically plausible brain architecture? Maybe also next to visual processing.
Yeah, that's a great question. So actually, there is now a lot of work that is mainly using DNNs because you can get these very powerful representations that both achieve very high accuracy in behavior, which is also quite important for getting good alignment, as we have seen and has been reported also by others. So what I think people are more exploring is like, how can we really change the architectures such that they are more biologically plausible? Because in a way, it seems that the AI field is converging to less biologically plausible, like think about transformers, or at least at the conceptual level, right? Even though the alignment is greater, and this is also like a puzzle that we have. But there are also some trends that say, let's try to constrain and make them more biologically plausible, like for instance, with having some constraints on the topography or having some constraints on how it processes information over time, and so on. And there are also efforts that are divergent from the deep learning comparison, let's say, but then they usually tackle like a specific cognitive task and how these are being processed in the brain.
Okay, thank you. How would the analysis pipeline change if you were to use sound or speech instead of videos, or like added sound to the videos?
Yeah, so we have done that actually in the example that I showed in the net to brain. So we used language, for instance, as one way of comparison. So from the human side, there is no change, right? Because you can get also fMRI responses, MEG responses, just the nature of the stimuli changes, right? So instead of having images or videos, so you have sound or you have text. This is on one side. And on the other side, what you need to change, of course, is the kind of models that you use. So you cannot use or you have to adapt a vision model. I wouldn't say you cannot use it. If your input stimulus is audio, for instance, right? So the set of models that you have to use are just targeted or that can ingest the input stimuli. And in net to brain, we have also audio models and video models with multimodality input and the language model. So the pipeline, like the concept of the pipeline doesn't change, it's the details that are important.
Thanks. One asks how to approach you for further questions.
Oh, just send me an email.
Okay, thank you. Um, do you have comments on the notion of privileged representation access in the brain and how that would impact the field in terms of literature, measuring alignment, via correlation of activations, as suddenly the correlation isn't a straightforward metric. The order of the axis matters a lot, and they provided a paper link. So I don't know, like if you've seen that. I haven't, so I need to check that.
Yeah, I don't see the link, but yeah, I mean, of course, one question is like we have representations and we are computing correlations, or even with encoding models is like these predictions. And of course, these metrics are not perfect, and each of them have their own advantages and their own limitations. So there is also like a strand of research that said like how we can get better metrics. So on one hand, I think we've been advancing quite a lot using these techniques, but even though they have these limitations, and one of these could be that, right? Like one could get like a very high correlation, and it might be just like co-founders and not the actual features that drive the correlation, and it could also be biased by data set and so on. But then on the other hand, we've also been able to understand quite a lot. So I don't think that we need to stop this, but rather put more efforts in enhancing the methods and being able to answer more scientific questions in a more meaningful way.
Mhm. Thank you. Do you think that these representation of models would change in case if person were moving? If I'm not wrong, movement includes some awareness of a space around you. I think they are referring to your scene study, and that they are looking at like affordances in the scene and how it temporally process. Like basically, if you put people in the scene rather than like just perceiving the scene.
Yeah. So I think that that task that and behavior that the person is performing will affect the representations probably. And this is like an interesting question that one could ask. And actually, we've been thinking about it. So you can, even in the static experiment, you can ask participants to perform different tasks, like to either identify objects or to try to imagine themselves navigating or do different things, right? So I do think that there is an impact here, right? To what degree, I'm not sure. I guess this is something we can hypothesize and then see if it holds with experiments.
Thank you. What types of encoding models have you used, and which ones were most successful?
So, I mean, what we usually do is just pure linear encoding. So what it means is that you have a particular model representation. So you have a particular architecture that you can get the activations and then just do linear encoding. And this is kind of like the crudest way of, and the simpler way of getting the encoding model, because it's just like the linear transformation from one space to another. So for instance, I can say that there are others, including participants in Argonauts, that what they did is use the DNN as the encoder model itself. So really to predict the brain data. Okay, so there are different things you can learn with this approach, which I think are also great. Like for instance, one beyond predicting, of course, because one can predict just for predict, like getting better predictivity score. But also, for instance, we had a participant that could trace back, so was predicting different activations of different brain areas, and then could trace back like, okay, for this particular brain region, this input, this part of the image was driving this prediction. And then things like FFA, was getting information from faces and so on and so forth. So this is something that he could unveil from his method.
Okay, thank you. The next attendee asked, very cool work. I'm not the most familiar with visual processing, but I would imagine the salience of the stimuli might influence which brain regions are recruited. I'm curious if your team is looking into this, maybe by scoring the saliency of the image, but I imagine this would vary greatly from human to human too.
Yeah, so at the moment, the saliency per se, we are not assessing. So one thing that we are linking to the interpretability of the model, so the model can also pick up certain regions of the image for the processing towards the final decision. And this one could be kind of like the saliency of the model in a way, which emerges from the model itself. And this is what we are trying to look into. But yeah, so one could think about of a more complex model to try to incorporate all these parameters. I think that would be really cool.
Mm-hmm. Thank you. I think this we at most can take one or two more questions. Are all internal representations of different kinds of models, LLMs, vision, convergent to a common space? For example, a representation of an apple in vision and LLMs would be similar or very different. Basically, from different modalities, I think you're asking.
So okay, so I think that there are different aspects in this question. So one thing is if you have a multimodal model, it depends on how it integrates the information. So if it integrates from the very early visual, then you have this convergence since the very beginning at the model level. And then what one could say is like, if I have models that integrate information at different levels as different hypotheses, how this correlates with, or how this aligns with the different brain regions, what are the differences? And then you can see, okay, so this is really like having like more semantics in this brain region. And it's really converging like what is more the understanding of the scene than the low level features, for instance, and so on and so forth. So at the model level, if you have, so it really depends on how the model is learned, because if you have like different modalities and they are all different streams, and only the alignment is done at the last layer, so you will have like very aligned representations in a common space at the last layer, but at the very beginning you will have like very domain specific, so very modality specific representations, let's say. And then one can use this knowledge to do the alignment with the brain and see how it's in the brain in comparison to the model.
Okay, thank you. And this will be the last question that we can take when the time. Which DNN models can better explain or model the dorsal pathway in visual cortex? Can you name some of them based on your experience?
Well, I mean, what I have seen in the results that I showed you is that models that are more related to global structure, 3D representation, so really a little bit also in the semantics, but even abstracting from the semantics and having like a more understanding of the position of the object, so really preserving structure and so on. This is what we have observed that are more predictive in the dorsal stream. And then from there, one could really try to craft it a little bit more in specific functions that one can hypothesize. But yeah, I would say like more 3D and maybe a bit of motion as well.
Okay. Okay, thank you very much, Gemma, for your time today. It was amazing, the talk and also the discussion. We got many questions and we almost went through half of it. And there are still more questions, but unfortunately we cannot take all of them. Anyway, thank you very much for your time and insightful talk. I'm sure everyone enjoyed both the talk and also the discussion that we had afterwards. Yeah.
Yeah, so thanks for
Everyone,
having
thanks for
me.
attending.
Yeah. Was a pleasure. Thanks for your questions.